let's review some of the facts that we saw for independence, right? Okay, so let's remember that two events A and B are independent if probability of A intersect B is equal to probability A times probability B, right? Alright, so this is if I have two events, right? If I have three events A, B, and C that are independent, right? Then you would have similarly that well, probably if the three of them are independent, right? What you have is probability A intersect B is equal to probability A times B, and then similarly probability A intersect C is equal to probability A times probability C, right? And the same thing for the B and the C, right? And also if I have the intersection of the three sets, three events here, A, B, and C, then probability of A intersect B intersect C is equal to probability A times probability B times probability C, right? Okay, so this is when you have two sets over here, and this is when you have three sets, right? And if you have three sets, the definition that we're using for independence really it is really the same independence, but if it's three or more sets, then technically you'd want to use the term mutually independent, right? But for us, we're not really going to distinguish between, say, when we have three or more sets, the different types of independence, say like mutual independence or pairwise independence, right? Well, the independence that we're going to be talking about in this class for three or more sets would be mutual independence. And basically, what that means for us is that if we have three or more sets, then your intersection, probability of intersection of the three sets here would be probability A times probability B times probability C, right? And similarly, if I had four sets, probability A intersect B intersect C intersect D would be the product of the probabilities, right? So that's how we're going to deal with if we have three or more sets here, right? If you're interested in the distinction between mutual and pairwise independence, I have it written up in the notes, right? And you can take a look, right? But really, for the purposes of this class, this is really what you should be using here, right? That if I have, say, three independent sets, then probability A intersect B intersect C is equal to probability A times probability B times probability C. Something else that we would need for independence is that if A and B are independent, right, then A and B complement are independent, A complement and B are independent, and then A complement and B complement are independent, right? Okay, and well, the proof of uh, this one over here, the second part B over here, it's in the notes, right? So you can take a look, right? Uh, but we're not really going to get into the details here, right? Okay, so the main thing over here is that if A and B are independent, then A and B complement are independent, A complement and B are independent, and A complement and B complement are independent. Next result for independence that we would need is this one here, right? So if A, B, and C are independent, right? Then A union B and C are independent, right? So you have these three sets over here that are independent, mutually independent. And what this is saying is if I form A union B, so this is a certain event, and then a next event C, right? Then the A union B and the C are independent, right? Okay, so the proof over here isn't long, so let's really just go through this, right? Okay, so I have what I want to do is I want to show that probability of A union B intersect C, right? Is equal to probability A union B times probability C, right? Okay, so that's really just that's really just a standard definition for independence, right? Which is this here, right? Okay, so what I want to do is I want to show that if I have this event A union B and the second event C, right? Then the A union B intersect the C over here is equal to probability A union B is equal to probability C, right? So this is, if I can go from here, this first line over here to this last line, then according to this condition for independence, I get that the A union B and the C are independent, right? Okay, so how do we go about this? Well, what you want to recall is, let me just remind you of something called distributive law, which you probably take for granted, right? So if I have A times B plus C, well, what you do is you take the A and multiply it by the B, take the A and multiply by the C and add, right? So that's a distributive law, right? And something similar holds for sets, right? So if I have A intersect B union C, what I can do is and take A intersect B, right? And I can take A intersect C, right? And then take the union of that, right? So very informally, if you want, you could sort of think of this intersection as say like a multiplication, union as addition, so you get the same kind of result, right? But that's anyway, so that's really looking at it extremely informally, right? But this is your distributive law for sets. So this is what we using over here, right? I have A union B intersects C, right? So this I can distribute this intersection, so I get A intersects C, union B intersects C, right? And now what I'm going to use is I just use my additive law, right? I have probability of the union of two events. And the additive law is additive law here. So I have the union of two sets A intersects C and B intersects C, and it's the union of those. So using this is probability, using this additive law, it's probability A intersects C plus probability B intersects C minus the intersection of A and C, A intersects C and B intersects C. So if you take the intersection of A intersects C and B intersects C, that's going to give you A intersect B intersects C, right? Now, what you're going to use is use the fact that the A, B, and C are independent, right? So if the A, B, and C are independent, you can split this intersection up into the product of the probabilities. Likewise over here, and likewise probability A intersect B intersect C, I can write as the product of these probabilities here, right? And then with this here, what I can do is factor out the probability of C, right? And then I have this inside the bracket, and this inside the bracket is probability A union B, right? Using the additive law again, right? Okay, so what I get is probability A union B intersects C is equal to probability A union B times probability C. And that, according to my definition for independence, shows that A union B and C are independent, right? Yeah, right. We have some electrical system that consists of four components, right? And the four components are shown here: A, B, C, and D, right? Okay, and the reliability, in other words, the probability of each component working is shown in the boxes here, right? So the probability of A working is 0.9, the probability of B working is 0.9, and the probability C working is 0.8, and D working is 0.8, right? Okay, so that's each component, right? Now what we want to see is overall if the system is working, right? Now this is the electrical system, so the idea over here is that if say I have current flowing, right? Uh, let's suppose say this one is working, right? But this one is not working. B isn't working, right? So if A is working, right, but B is working, then you, if you want, you have a break in your circuit, right, and the current wouldn't be able to flow, right, past the B, right? Okay, so in order for your system to work, right, both the A and B have to be working, right? Okay. Right, so that's the first thing, right? Now, again, thinking about the current flowing, right? If your current is flowing, now suppose the A and the B are working, right? And your current flows through, okay, through A and B, right? Now, if, say, for example, D is not working, but C is working, right? Then you're still good, right? Because your current can flow through A, B, and C as well, right? And then complete, right? Okay. However, so what this is saying, what I'm saying here is, anyway, let me, okay, so let's A and B have to work, and that's an example. If D is not working, and then your overall your system is working because your current can flow through A, B, and C, right? If, however, both of these are not working, then when your current is flowing, there's a break over here and there's a break over here. So your current can't flow through, right? In which case your system is going to work, right? So the idea over here is in order for this system to work, A and B must work, and one of these two have to work, right? So either the C must work, or the D must work, or both of them. Okay, so either one or both of them, but you can't have none of the C or the D not working, right? Because then the system wouldn't work, right? So in order for this system to work, A must work and B must work, and C or D must work, right? All right. Okay, so and in fact it's stated in the question, right? Your system works if components A and B work, right? If components A and B work, and either of components C or D work. So that's really what I just said, right? What you want to get is, first of all, the probability that the entire system works, right? So let's focus on part A to start off with, right? Okay, so we're gonna use events here, right? So we say A is the event that you, this first component works, right? B is, and similarly, B is the event that component B works, and likewise we define events C and D, right? Okay, so the probability that the entire system works, right, is probability A intersect B, right? So how you want to read this is that A is working and B is working, okay, and then and C or D is working, right? Which is what's described over here, right? Okay, so one more time, what we want is for a system to work, A and B must work, right? So events A and B must occur, right? In other words, we're looking at the intersection of the events A and B. And C union D, right? So C union D is C is component C is working or component D is working, right? So what we want is A and B working and C or D working, right? And we have this now expressed as events, right? Okay, so once we have this setup over here, what we're going to do is we're going to use the rules that we know for independence, right? And some of those I just talked about a couple of minutes ago, right? Okay, so what I have first of all is the intersection of three sets, right? I mean, I have it grouped as A intersect B, right? But this is A. You could regard this as the intersection of three sets, right? A, B, and C union D, right? Okay, and if I have three events intersection of three events, then really what I'm using is I'm using this type of result, right? Okay, if you have the intersection of three events, you multiply the probabilities of each one, right? Assuming you have independence, right? And this is, we assuming that in the question that your components are working independently, right? Okay, so that's how we go from this line over here, right, to the line below, right? Okay, and now what we need to do is work this out, right? Now how I have this worked out over here, right, it's not, it's correct, right? But there's no real need to in fact take complements over here, right? So you can take a look at the notes at what I did, but let me show you an easier way to do this, right? Got to this point where we have probability A times probability B times probability C union D, right? Which is what this line is here, right? Now to work out the probability C union D, right? All I do is I just use additive rule for union of events, right? And this is additive rule as probability C union D is probability C plus probability D minus probability C intersect D, right? And this over here, right? What I can do is the probability C intersect D. Given that the C and D are independent, I can write this as now a product of probability C and probability D, right? And the goal over here is, notice this expansion here, right? The goal was to get down to an expression like this, where now this is just probability of each of the individual events, right? I have no intersections or unions or anything, right? These are just all given to me in the question, right? So it's given to me in the question that probability of A working as 0.9, probability of B working as 0.9, C is 0.8, D is 0.8, and likewise I use probability C, probability D are both 0.8 over here, right? Okay, so I get this numerical expression and I just evaluate it and I get my answer, which is 0.7776. Let's look at the second part of this question, right? What we just found was we found the probability that the entire system works, right? And the probability that the entire system works is probability A intersect B intersect C union D, right? So this means that A is working, B is working, and C or D is working, right? And now what we want is we want a probability that C is not working, given that the entire system works, right? Okay, so if we want to calculate a probability of an event occurring, given that next event has occurred, right? What we need to do is we need to determine a conditional probability, right? Okay, so the probability that C is not working, given that the entire system works, right, is probability of the event C is not working, so the event of C not working is C prime, C complement, yeah. Okay, and this is, so we want probability of C prime given that the entire system works, right? But what is the event of the entire system working, right? The event of the entire system working is A intersect B intersect C union D, right? So what we want is probability of C complement given this event over here that the entire system works, right? Okay, so once we have this over here, we want to calculate a conditional probability, and we use our definition of conditional probability to calculate this, to calculate the conditional probability, right? This conditional probability here, right? What we use is use this definition of conditional probability. So probability of C complement given this event is the probability of C complement intersecting this big event over here, right? Divided by the probability of the event A intersect B intersect C union D, right? So let me remind you about your distributive law, right? Which I just talked about. So if I have A intersect B union C, that's equal to A intersect B union A intersect B, A intersect C, right? So you take the A intersected with the B, you take the A and intersected with C, and you take the union of those, right? All right. Okay, so I want to work this out here, right? So, well, the nice thing is we already worked out what this bottom is over here, right? So this is the probability that the system is working, right? So we calculated that in part A, right? That was 0.7776, right? Okay, but we still need to work out the probability of this top event over here, right? Now notice this is some intersections and unions, right? So what I need to do is let me just work out what's inside this bracket over here, right? Now what this section of A intersect B intersected with C union D, right? What we want to do is, because I have a union inside there, I want to use my distributive law here, right? Okay, so as I said, I'm working inside the bracket over here first, right? So what I have is, this is A intersect B intersect C, right? Union A intersect B intersect D, right? So you want to think of that you're really just grouping the A intersect B into one event, and you're taking that group and intersecting it with C, and then intersecting with D, and then taking the union of those, right? Okay, so once I have that over here, right, now again I need to use my distributive law, because what I have is C complement intersected with a union over here, right? Okay, so what I need is C complement intersected with this first event over here, and then C complement intersected with this event over here, right? Now, when you take let's take a more careful look at this intersection of the C complement with the union here of these two events. One event is A intersect B intersect C, and the next one is A intersect B intersect D, right? Okay, so C complement intersected with this union, you use the distributive law, so it's C complement intersected with the first event A, B, and C, and then C complement intersected with the second event A, B, and D, right? Okay, right. So this is going from here to here is using the distributive law, right? Now you want to notice inside this first intersection over here, right? So this first event, what you're doing is you're intersecting C with C complement, right? Now C intersected with C complement is the empty set, and the empty set, once you intersect anything else with the empty set, you're just going to get the empty set, right? So this first event over here, the C complement intersect A intersect B intersect C complement is just going to be an empty set over here, right? Okay, and then this one just comes down, and what you have is union of an event with the empty set, which is just the same event over here, right? So that's how I go from this line here, right, with the C complement intersect of these two events to just A intersect B intersect C complement intersect D, right? That this over here is the same. What's inside the bracket, A intersect B intersect C complement intersect D, is really just the same as this over here, because you can change the order of the intersection of events. Now with this here, I need to work this out, right? Now working this out over here, we just talked about this, right? The A, B, C, and D are independent, right? And if the A, B, C, and D are independent, it means that the A, B, C complement and D are also independent, right? And because they're independent, I can in fact write these as a product of probabilities, right? So probability A times probability B, probability of C complement plus times probability of D, right? And the probability of C complement I can write as 1 minus probability of C, right? Okay, so once I have that now, I just insert what my probabilities are. The probability A is 0.9, probability B is 0.9, probability C is 0.8, probability D is 0.8. Okay, and then you just work out this numerical expression to get your answer, which is 0.1667. What we're going to look at now is you're going to look at Bayes' rule, right? And well, before we get to Bayes' rule, what we're going to talk about is the law of total probability, right? So that's what we're going to talk about first, right? And then, so first result over here is for law of total probability, and then we'll do an example of we'll state what Bayes' rule is over here, right? Okay, so first thing is law of total probability, right? Now I have it described here in the notes somewhat formally using sets, right? But let me just use an example so that you can probably see what this law of total probability is, right? Okay, so and we will get to this example in a little while, right? In more detail to actually work it out, right? But I'm using the rubric over here, right? Okay, so I have an assembly plant. I have an assembly plant where machines B1, B2, and B3 are making products, right? Okay, so of the products made, 30% made by machine B1, 45% are made by machine B2, and 25% are made by machine B3, right? Okay, so you can consider S over here, his sample space, is the set of products made, right? And set of products made over here, right? A product is either made by machine B1, machine B2, or machine B3, right? So in a sample space, if your sample space is a set of all products, right? This B1 over here, we could regard as the event of the product being made by machine B1, right? And likewise, B2 over here is the event that the product was made by machine B2. And likewise here for B3, right? Okay, so a product is made either by B1, B2, or B3, right? Okay, and it's not made by anything else, right? And then also a product cannot be made by both machines B1 and B2, right? So what I'm saying here is that because a product is either B1, B2, or B3, how you want to read that in terms of sets or events is that you want to read it in terms of events is that B1 union B2 union B3 is equal to S, right? Of all the products that are made, right? The products that are made by machine B1, the products that are made by machine B2, and the products that are made by machine B3. those consist all your products, right, that are made, right? And all the products that you made is sample space, right? And over here, what this says, how you want to read this is that you have a product could be made by machine B2, it could be made by machine B3, but it can't be made by both, right? Okay, so B2 intersect B3. Products made by machine B2 and products made by machine B3. That's the empty set over here, right? Question is we considering the event of defective products, right? Okay, so we have we're looking at you have it's possible that some of these products made by one of these machines over here, right? It's going to be defective, right? Okay, so of your set of products made, right, by the factory, a certain subset of those would be defective, right? And that subset is your event A here, right? So A is the event that the product is defective, right? One of the products is defective. Now, if you have a product made by the plant and that product is defective, right? Well, common sense, if you have three machines making the products B1, B2, and B3, it means that if the product is defective, either it was made by machine B1, it was made by machine B2, or it was made by machine B3, right? Okay, so what that means is that the set of all products, right, that are defective, right, either they came from B1 over here, or they came from B2, or they came from B3, right? And this is what this line is saying over here, right? Your subset of defective products consists of the defective products made by machine B1 together. The subset of all defective products would be the ones made by B1 together with the ones made by B2 and the ones made by B3, right? And that is in fact all your possibilities for your defective products, right? Because you only have products made by B1, B2, and B3, right? Okay, so the A is split between among the B1, B2, and B3, right? Okay, so one more time, right? So this here is S is the set of all products made by the assembly plant, right? And those products are split into those made by B1, B2, and B3. So that's what this Venn diagram is doing for you, right? And now what I have is a separate event, an event of defective products, right? So I have a separate event, and that separate event over here I'm denoting by this green shaded subset, this green event over here, right? Now, what you want to notice is that this green event A that represents the defective products, it intersects B1, so that's this part over here, right? It intersects B2, which is this part over here, and it intersects B3, right? So the entire A consists of the part where it intersects B1, the part where it intersects B2, and the part where it intersects B3, right? Okay, now you want to notice with these parts over, right? So you want to notice with these parts over here, because, for example, B2 and B3 have nothing in common, right? What that means, what that implies is that A intersect B2 and A intersect B3 will have nothing in common, right? Okay, and similarly, A intersect B1 will have nothing in common with A intersect B2, right? Okay, so what that means is that A being expressed as this union, this is a disjoint union, right? These three sets are mutually disjoint, right? If you take the intersection of any A intersect B1 with A intersect B2, right, that would be the empty set, right? Now, given that these are disjoint events, right, what we can do now is you can use your third axiom that says that third axiom of probability, that the probability of A is equal to probability of A intersect B1 plus probability intersect B2 plus probability intersect B3, right? There should be a 3 over here, right? I notice you can do this because you know that these sets over here, right, the intersect B1 and the intersect B2, they're mutually disjoint, right? Okay, and once you have that, right, what you can do is you can write this probability A intersect B1 use your product rule to write this as probability B1 times probability A given B1, right? Now, why would you want to write this probability of intersection as probability of B1 times this conditional probability? Well, why you want to do that is because that's sometimes is usually just what's given in the question, right? Okay, so what's given in this question over here, right? Uh, that we use in this example, right? Well, we know probability of the product being made by machine B1 is given in the question is 0.3, right? Okay, because they literally state that in the question, right? 30% of the products are made by machine B1, right? Okay. Now, this 2% over here, right? So, from past experience, 2%, 3%, and 2% of the products made by each machine are defective, right? So, what this 2% or probability 0.02, right? This is a probability that the product is defective given that it was made by machine B1, right? So, what you're given over here is you're given a conditional probability, right? So that's why you'd want to go from here to over here, right? Now, this statement, in other words, this is why you'd want to write the probability of the intersection of events as using conditional probabilities like this, right? Now, okay, so let's work out this problem here with the three machines making products, right? Okay, so what is set up over here? We talked about, right? In assembly plant, machines make products, right? And any given product made from the assembly plant, right? There's a 0.3% that is made by machine B1, 0.3%, 0.45% probability that is made by machine B2, and 0.25 probability that was made by machine B3, right? Okay, so first thing we could do over here is let B1 be the event that the product was made by machine B1, right? And let B2 be the event that that the product was made by machine B2, right? So in this in your sample space S over here of the products made by the assembly plant, right? B1 over here is products made by machine B1, B2 over here is products made by machine B2, and B3 over here is products made by machine B3, right? Okay, and now they give you that, right? And now they tell you something about defective products, right? First of all, they tell you that the products made by machine B1, 2% would be defective, and likewise for B2 and B3, 3% and 2% respectively would be defective, right? Right, so what you want is, and you choose a product randomly, right? What you want is the probability that it is defective, right? Okay, so this is what we're interested in, right? We're interested in the probability that product is defective, so we let A be the event that product is defective, right? Now the event that the product is defective is a subset of my sample space, right? Because if you want probability that a product is defective, what you're doing over here, A is a set of all defective products, S is your sample space, and you want the probability of the event A occurring, right? So the probability of basically choosing a defective product, right? So we want probability of A, right? Okay, so we want probability of A, and to work out this problem, because we're given conditional probabilities over here and normal probabilities, what we're going to be doing is we're going to be using a law of total probability to work this out, right? Now, before I get into this law of total probability, right, I can illustrate what's going on by a tree diagram, right? And this tree diagram is particularly useful because, in fact, you could probably do almost all your calculations here using this tree diagram, right? Okay. Right. Okay, so how you want to read this diagram is that first of all, you're choosing a product, right? And if you choose a product, right, the product could be made by machine B1, could be made by machine B2, or it could be made by machine B3, right? So that's the first thing, right? And then over here, right, if it is made by machine B1, right, then it could be defective, right? So A is the event of being defective, or it may not be defective, right? In which case you have A complement, right? Complement over here is assuming that B1 has already occurred, right? Okay, right. So in this, and likewise from over here for the B2, right? You have a product, right? It could come from B2, and it could be defective or not defective, right? So this should be A over here, not A prime, right? And likewise, this should be A over here, not A prime, right? So this is A prime, A prime. So the product made by machine B2, it could be defective or it could be not defective, and likewise for the B3, right? Okay, now in this tree diagram here, right, what we could do is we could put in the probabilities, right, on the edges, right? Okay, so, well, if you have a product, you choose your product, well, what's the probability of it being made by machine B1, right? Well, that's given in the question. That's your 0.3 over here, right? Okay, and the probability that's made by machine B2 is this 0.45, which is a 45% here, right? And likewise, probability that the product was made by machine B3 is 0.25, right? Okay, so these over here, these are normal probabilities if you want, right? Now, well, given now over here, once you have a product and now you know that it was made by B1, right? Well, what's the probability of it being defective, right? Well, the probability of it being defective is in fact now a conditional probability, right? You want probability of defective given that the product was made by machine B1, right? So what you have is a conditional probability over here, right? So in your tree diagrams, your first edges over here, the weights of these first edges, right? These are normal probabilities, but afterwards what you're going to have is you're going to have a conditional probability, right? Okay. Alright, okay, so probability of being defective given that B1 has occurred, well, that is this 0.02 over here, right, which is written over here, right? Okay, right, so now what we want is, well, we may want, well, what's the probability of it not being defective given that it was made by machine B1, right? And I mentioned this a little earlier, right, that if I want to get the probability for this edge over here, right, I can get it by using the fact that A complement, well, is the complement of A, right? But this is now for conditional probabilities, but this complement formula also holds for conditional probabilities, right? So what I'm saying over here is that if probability A given B1 is 0.02, right, then the probability of A complement given B1 would be 1 minus this probability, and 1 minus 0.02 is 0.98, right? Okay, right, so typically probably in these questions what you'd be given is one of these over here, and you'd need to figure out what the probability is for this this second edge over here, right? Okay, and in this case we're doing it via complements, right? Complements for conditional probabilities, right? Okay, and similarly for B2, right? Your question for B2, right? The probability of it being not defective, remember this should be a over here. The probability of it, sorry, being defective, right? Given that it was made by machine B2 is just 0.03, right? And likewise over here, the probability of it being defective, given that it was made by machine B3, this is 0.02, right? Alright, so what we want is the probability of the product. If we choose a product, what's the probability of it being defective, right? Now the probability of it being defective is, well, it's this case over here. Now this case is, it's defective and it was made by machine B1. It's this case over here and it was made by machine B2, and it's this case over here and it was made by machine B3, right? Okay, so this is what your law of total probability is saying, right? The probability of it being defective is the probability of it being defective and made by machine B1, which is this case over here. Probability of it being defective and made by machine B2, which is this case over here. And probability of it being defective and being made by machine B3, right, over here, right? Okay, but we could state, if you want, you could just state your law of total probability here now, right? And to get the probability of it being defective, now you're just using your law of total probability. You know the probability to B1, B2, and B3. That's just 0.3, 0.45, and 0.25 respectively. And you know the corresponding conditional probabilities, which would be the 0.02, the 0.03, and the 0.02, right? Okay, so you can feed in all your information over here, and this will give you the probability of a product chosen at random is defective, right? Okay, so this is using law of total probability, right? But in fact, you could also work it out from your tree diagram over here, right? Okay, so from your tree diagram, the probability of it being defective is this case over here, this case over here, and this case over here. Remember, I have a typo, right? So this should be A here, and this should be A here. Right, so I have 3 cases. Now, what's the probability of ending up in this case over here, right? Well, this meant that first the product was made by machine B1, then it was defective here, right? Okay, so this over here means if you got to this point, it means that it's defective and made by machine B1, right? So, well, so this over here, at this point over here, the probability to get in at this point is probability A intersect B1, right? Now, probability A intersect B1 by product rule is probability B1 times probability A given B1. In other words, it's the product of the probabilities on these edges over here, right? Okay, so to get the probability for A given B1, right, you take the probability on this first edge over here and then your second edge here, right? Likewise, and remember this is supposed to be an A. The probability of having defective here for this case is the product of the probability 0.45 and 0.03, and the probability of having an A over here is the 0.25 times the 0.02, right? Okay, and you have these are 3 cases over here, right, of defective, right? This is over here is defective made by B1. This here is defective made by B2. This is defective and made by B3, right? Okay, so to get defective overall, right, what you need to do is you need to add those 3 probabilities. So I have it written here: this one, this one, and this one, and that would give me my answer, right? Okay, so and that's really working out law of total probability using your tree diagram over here, right? Alright, okay, so we saw an example of law of total probability, right? And an example of law of total probability using it is that the probability of A we get in terms of conditional probabilities here, right? And then normal probabilities, right? Okay, so now what we want to talk about is Bayes' theorem, right? Now Bayes' theorem, if you want, is sort of an extension of law of total probability, right? What you're going to do is in Bayes' theorem you will use law of total probability, right? Okay, so to give you an idea what Bayes is, I'll continue with this example with the products being made by 3 machines, right? And where we interested in if our product is defective or not, right? Okay, so for that example, what we're considering now is we want to get the conditional probability of B3 given A, right? So, right, so what we saw already was, for example, here, right? Okay, so this over here, this probability of A given B1, right? This is the probability of a product being defective given that it was made by machine B1, right? Right, so likewise over here, this is supposed to be A, right? This here is the probability of A given B3, right? Probability that the product is defective given that it was made by B3, right? Now, what we want is we don't want, so this over here, this probability A given B3 is this 0.02, right? Notice what we want over here now is we reversing the order here for your conditions, right? We want the probability B3 given A, right? So one more time, this is over here probability A given B3 was the 0.02, right? What we want is probability B3 given A, right? And we can read that, explain what it is what we want is given that the product was defective, right? What is the probability it was made by machine B3, right? Okay, so this is using Bayes over here, but as I said, Bayes uses the law of total probability that we just saw, right? Now, okay, so we want to get this conditional probability B3 given A, right? Now probability B3 given A, this is a conditional probability. I can use my definition here of a conditional probability to work it out, right? And notice on the bottom over here, I have probability of A, right? Now we already know what probability of A is. We worked that out already, right? Probability of A is when you multiply these two edges, the 0.3 by the 0.02 over here, you multiply the 0.45 by the 0.03, so you multiply these two edges, and then you multiply these two edges, the 0.25 by the 0.02, right? And when you add up this product here with this product with this product, what you get is you get the probability of A, right? So the probability of A consists of probability of A consists probability of defective is defective and made by machine B1 plus defective and made by machine B2 and defective and made by machine B3 over here, right? Okay, so that's all. That's how you get the probability of defective, right? Probability of defective is the sum of those three cases here, right? And each case is a product of the edges here, if you want, right? What we want is probability of defective, right? And probability of it being made by machine B3 given that it was defective, right? Now, given that it was defective, probability of defective was the sum of these three cases, right? And now what I want is I want to get the probability it was made by machine B3, right? Now, of these three cases, these two over here, right? This is the product of these two is for machine B1, right? The product of these two over here, this is for machine B2, and the product of these two over here is for machine B3, right? Now, if we want, so for defective, given that it's defective, and it was, given it was defective, right? What's the probability it was made by machine B3, right? What we want is out of these three cases over here, right? This product 0.3, 0.02, this product 0.45 times 0.03, and this product 0.25 times 0.02. We want the probability that you actually used this edge over here, right? So really what we're going to look at, so probability of A, right, as I said, consists of these three cases, which is probability of A is these three cases when you add them up over here, right? And probability of defective and made by machine B3 is one of these three cases, right? It's this last case over here, right? The 0.25 times the 0.02, which is this, right? Okay, so of these three cases where it's defective, where defective and made by B1, defective and made by B2, and defective and made by B3, right? The probability that it was made by B3 given that it was defective is you take in this case over here and you divide it by the sum of all three cases, right? And that's how you're going to get probability of B3 given it was defective, right? So I guess one more time, right? So we want probability given it's defective that it was made by B3, right? This is defective and made by B1. This is defective and made by B2, the product of these two edges. This is defective and made by B3, right? And out of the sum of those three cases, what you want is this third case over here, right? So you take this third case over here and you divide by the sum of the other, by all three cases, right? And that's really the idea of where this is an example of using Bayes, right? Okay, so that's using this example over here, but we could look at it a little more formally, right? So we want conditional probability of B3 given that A has occurred, right? So the probability that given that the product is defective, that it was made by B3, right? So first thing you could do here is you just use your definition of conditional probability. Now this probability of A on the bottom here, we already worked out, right? We already worked out that we got from the law of total probabilities. So this over here, as I said, is you take in these two edges, right? And these two edges over here, this one, the 0.3 and the 0.02, that would be this product here, right? And then you take these two edges, the 0.45 and the 0.03, and that would be this product here. And the 0.25 and 0.02 is this third product here on the bottom, right? So that is probability of A. We worked out that for lower total probability, right? And now what we need to do is we need to work out this probability B3 given A, right? Now probability B3 given A, right? We want to write this in terms of a conditional probability, and we want to write this using A given B3, right? Because this is what's given to us, right? Probability A given B3 is given to us, not probability B3 given A, right? Okay, so we want to write this probability of B3 intersect A, right? In terms of probability B3 times probability A given B3, right? So we're working out the top now. But this top over here is really just the product of these two edges here, right? So this is probability B3 and this is probability A given B3, right? Okay, right? And when we do that, right, for the top over here, this is the 0.25 times the 0.02. The bottom over here, as I said, is the sum of your three products here, right? And your required conditional probability is, well, you just work it out numerically and you'll get your answer here, which is 10 on 49, right? Okay, so this example over here is illustrating Bayes' rule, right? Of Bayes' rule, right? Or Bayes' theorem, right? Okay, so what we have is similar to law of total probability. We have events B1, B2, B up to BK forming a partition of a sample space, right? So in this example of three machines, right, the partition of your sample space is done by B1, B2, and B3, right? Remember what the S is. The S is all products made by the factory, right? The B1 is the products made by machine B1, B2 is products made by machine B2, and B3 is products made by machine B3, right? Okay, so this here is an example of a partition, right, of a sample space, right? Partition of a sample space means that B1 union B2 union B3 is equal to S. And if you, this union, the events over here are all the pairwise disjoint, right? B1 intersect B2 is empty, B2 intersect B3 is empty, and B1 intersect B3 is empty, right? So this is an example of a partition of a sample space, right? Next condition in Bayes is that you require that the probability of each of the events B1, B2, B3, and so on, right? The probability of each of those events is not equal to 0, right? Why you want each of those probabilities to not be equal to 0 is really, remember what you're doing is you're working with these conditional probabilities over here, right? See, A given B1 is defined as probability A intersect B1 divided by probability of B1, right? So you'd want this probability of B1 to be non-zero, right? So, and that's for all the cases, right? So that's why you'd want your probabilities of the BIs to be non-zero, right? Okay, and then similarly, we have some event A in S, right? And we want the probability of that to be not equal to zero, because again, what we're looking at is a conditional probability now. Now, given A has occurred, right? So that's for the same reason we want this probability to be non-zero. And in your question, typically what you're given is probabilities like this, right? Probability, say A given B1, probability A given B2, and so on, right? But what we want is in Bayes, right? What you're going to be doing is you're going to be reversing the conditional if you want, right? Instead of probability A given B1, you want probability of, say, like B1 given A, right? And how you do it is via this sort of formula here, right? So just as what we did in the previous example, right? Right? If I want probability of, say, like a B3 given A, you use your definition of the conditional probability, right? On the top over here, what you have is intersection probability of the intersection of B R with A, right? And then on the bottom over here, what you have is probability of A. This probability of A you get from your law of total probability, which gives you this line. And this top over here, you get in terms of product rule, right? Using one of the conditionals that's given to you, right? Okay, so this is your formal statement of Bayes' rule, right? But really, when you're working out Bayes' rule in these particularly simple cases, right? And the simple case that we just looked at was probability of B3 given A. How you'd work it out is you'd want probability of A on the bottom, and the probability of A on the bottom is you take these two edges, multiply, you take these two edges, multiply, you take these two edges, multiply. So you add up all your cases where you have probability of A, and that gives you this. And then what you do is you take your two edges, that's what you want, right? Here what I want is the B3, so you take these two, multiply them, right? And then you take that 0.25 by the 0.02, right? Which is this, and then you divide it by the sum of all three cases for probability A, right? Which is down here. Okay. Right, so that is what Bayes looks like, right? And it's pretty helpful to use a tree diagram when you're working these out. Talk about what a random variable is, right? So before I get into, say, a formal definition, let's say consider this basic example here, right? Okay, so I have an experiment where I flip a fair coin, well, I flip a coin twice, right? So a sample space, which would be set of possible outcomes, would be two heads, heads or tail, tail heads, and or tail, two tails, right? All right. Okay, so with this experiment and with this sample space here, right? Well, with the experiment, right, what we could define is we could define a random variable, and your random variable is counting the number of heads, right? Okay, so for example, if you perform this experiment and you get head first and then a head again, right? So you get head head. Then for that outcome, what you get is you get a value of a random variable. You get a value of 2, right? Okay, so each of your outcomes over here, you're going to get a certain value for your random variable, right? So for example, next example is let's say I do my experiment and I get head tails, right? So in that case, the value that I get for this random variable would be number of heads, which is 1, right? Likewise, for this one over here, right, the number of heads, right, is 1. And then for this outcome over here, the number of heads, so the value of x is 0, right? Okay, so what you want to notice over here is that for each possible outcome in your sample space, for this random variable over here, you're going to assign a unique number to it, right? Okay, so and you can see, you can describe that assignment using this table, right? So for head head here, right, for the outcome head head, right, what you get is you get a value of 2, right? For outcome head tail, you get a value of 1, and so on, right? So when you have two tails, the outcome that you get, number of heads, is 0, right? So each outcome over here has a number, a unique number associated to it, right? Based on what the definition of a random variable is, right? But probably more importantly is that each number over here has a number assigned to it, and this is in fact defining a function for you, right? And that's how you can view a random variable, right? A random variable is in fact a function, right? It's a function on your sample space, right? Okay, and the particular function on this sample space over here, right? So these are the elements of your sample space in this table, and this is omega over here is just referring to an outcome. So for example, here omega is 2 heads, right? And x omega means that you evaluating for this function, you evaluating the function for the outcome omega, right? This is really some sort of somewhat fancy notation. Really, all you have is if you have this outcome head, your function is assigning a value to, right? So for head tails over here, your function is assigning a value 1, right? And for say tail over here, your function is assigning a value 0, right? So what a random variable is? A random variable is a function on sample space, right? Okay, so this is its definition over here, right? A random variable is a function that associates an outcome to each element in your sample space. Okay, so for this example, when we flip a coin twice, right, and we got the sample space, and we consider the random variable, which is the number of heads, right? Your possible outcomes for this random variable would be either 2, 1 in these two cases, and then 0 in this case, right? So the possible values that you get for this random variable would be 0, 1, 2, which is obviously a finite set, right? Okay, so let's see a next example, right? So now I flipped the coin 3 times and I'm recording the results, right? And I'm now considering a random variable which is defined as number of heads minus number of tails, right? Okay, so for example, for this outcome over here, which is head, tails, right? The value of the random variable would be number of heads, which is 2, right? Minus number of tails, which is 1, right? So you get 2 minus 1, which is 1, right? Okay, and what this is, okay, right? So this is this is the random variable here, and remember the random variable is a function on your sample space, right? So what's the sample space? The sample space are your possible outcomes, and I wrote it here in this first column of this table. These are the 8 possible outcomes from this experiment here. And for each outcome, you have a certain value, right? Based on what the definition of this random variable, right? So, for example, over here, when I have the outcome 3 heads, right? The value of y that I get would be number of heads minus number of tails. Here I have 3 heads and I have 0 tails, so I get 3 minus 0, which is 3, right? Okay, so for each outcome, you get a certain value, right? And the set of possible values for this random variable, you can see from your table over here, it's going to be 3, right? 1, minus 1, minus 3, right? So you have 4 possible values for this random variable, and this is a finite set. Okay, so let's look at a more involved example, right? Okay, so what we're going to do here is we're going to flip a coin until we actually get a head, right? Right, so what would be outcomes over here, right? Well, you could flip the coin, you get a head, right? So you flip it until you observe a head, and what this means is that you flip until you observe a head, and then you'll stop, right? Okay, so here I get a head, right? And therefore I stop, right? So I get this outcome, right? But suppose I got a tail first, right? The experiment is saying that I need to keep flipping until I get a head, right? So I get a tail first and I flip again, right? And it's possible that on the second flip I will get a head, in which case I'll stop over here, right? Okay, or you could flip the first time and get a tail, right? In which case you need to go again, right? You flip a second time, and if you get a tail, you need to go again, right? And if you get a head on the third flip, right, then you'd stop, right? And you see what the type of outcomes you're gonna get, right? The type of outcomes you would get is basically you're gonna get a sequence of tails, and then finally you're gonna get a head, right? So you can get a tail, then a head, in which case you stop. You can get two tails, then a head, and you stop there. You can get three tails and a head, and then you stop there, right? Now, you want to notice that this sample space over here is not a finite sample space, right? Because you could flip your coin, say, 10 times, right, and get 10 tails in succession, right, and then finally get a head, right? Probability of that happening might be probably pretty low, right? But it still could possibly happen, right? You could flip the head 100 times, flip the coin 100 times, and you can get, say, 99 tails and then one head, right? Okay, so what I'm saying over here is that this sample space over here is not finite, right? Okay, any number that you could think of, say, uh, 100,000 means that a possible outcome would be that if you flip the coin 99,999 times and you get a tail, and then you flip it the last time and you get a head, right? That would be the outcome, right? So this here is a sample space that is a little different from what we saw, right? And this is a sample space of it's not a finite sample space, right? This over here, this is sample space is infinite, right? But this is actually something called countably infinite, right? And I'll explain in a little while what countably infinite is, right? Okay, so for this sample space, for this experiment, I can define a random variable, which is the number of tails I got before the first head, right? Okay, so for example, over here, when I flip, right, and I get a head and I stop, right, I didn't get any tails before. So the value for this over here is 0, right? In this case over here, I get a tail on the first flip and then a head on the second flip. And this over here, I got one tail before the first head. So the random variable here is 1, right? And also this case over here with tail, head, right? The random variable is the number of tails before the head, right? And the number of tails before the head over here, this is in fact 2, right? So the value of the random variable over here, this is 2, right? Okay, the value of the random variable over here is 3, right? Okay, so your elements in your sample space we can list over here in this column, right? We can't list all, so we use these dots to indicate a pattern, right? So possible outcomes is head, head, 2 tails and a head, 3 tails and a head, and so on, right? And these are the corresponding values of a random variable, right? And in this case, again, the possible values of your random variable, this is a countably infinite set, right? So that's different from the say the cases that we looked at before, right? So the case when we flip the coin 3 times, right? The set of possible values, you had 4 possible values, right? This was a finite set. In this case, the possible values of the random variable is in fact countably infinite, right? Right, okay, so we're using, say, countably infinite and uncountably infinite or uncountable to describe 2 different types of infinity, right? A set is countably infinite if basically it looks like natural numbers, right? You can put a countably infinite set. You can create a bijection with a set of natural numbers, right? So informally speaking, a countably infinite set means that you're going to have one, then you're going to have a next one, then a next one, and a next one, and so on, right? Okay, so example of a countably infinite set is, for example, 0, 2, 4, 6, 8, and so on, right? This over here, you're counting one after the other, right? Informally, or what you could realize is that you can create a bijection between your natural numbers over here and your set of even numbers here, right? Okay, on the other hand, say if you have an interval like this, right? So real numbers, right? And if you consider interval between 1 and 4, right? Where you probably don't need to include, doesn't make a difference, but if I don't include the 1 over here and I do include the 4, right? This interval over here, this is something called countably infinite, right? The idea over here is that between 1 and 4, you have lots of things, right? You have, say, like 2, you have 2.1, you have 2.01, you have 2.001, and so on, right? So there's in fact an infinite amount of real numbers between 1 and 4, and the interesting thing is there's more real numbers between 1 and 4 than you have, say, numbers from natural numbers 0, 1, 2, 3, and so on, right? Okay, so basically, countably infinite means that you more or less you have a sequence, right, of elements in your set, and uncountably infinite first would mean that somewhere you have some sort of interval of your real numbers, right? Similarly, the set of real numbers, which is, if you want, just your long interval of real numbers, that also, well, that's the interval, and that is uncountably infinite, right? Anyway, so the point about this is that a random variable is, we're going to have two types of random variables that we look at in this class, right? We're going to have discrete random variables and we're going to have continuous random variables, right? Okay, and a discrete random variable is a random variable when the set of possible outcomes is finite. Okay, so for example over here, right, for this experiment over here, and for this random variable w, which is number of, sorry, for this experiment over here, right, where you flip the coin 3 times, right, the set of possible outcomes for a random variable would be 3, 1, -1, and 3. This is a finite set. So this is an example of a discrete random variable, right? This experiment where even though you have a infinite set over here, when you look at your outcomes, right, the outcomes, it's a sequence here of outcomes. It's an infinite sequence, and this over here, the set of outcomes over here, this is countably infinite, right? So this random variable over here, this w over here, is also a discrete random variable, right? Discrete random variable we just saw is a random variable when you set of possible outcomes for the random variable is finite or countably infinite, right? On the other hand, random variable is said to be a continuous random variable if your set of possible outcomes, right, would consist of all numbers in an interval, right? And this interval could be a finite interval, such as the interval that we looked at, which was 1 to 4, right? Or possibly an infinite interval, right? So by infinite interval, I mean, say, like all of real numbers, that's an interval of infinite length, right? All right. Okay, so an example of a continuous random variable is this example over here, right? We have a factory that's manufacturing compressors, right? And for the set of compressors, the sample space of which consists of the set of compressors made by the factory, right? What we want to do is we want to define a random variable which is the lifetime in days of one of the compressors, right? Okay, so the lifetime in days, right, of the compressor, right, it could be 0, right, which means that the compressor was malfunctioned and was defective to start, right? Or the lifetime, it could be, say, 10 days, it could be 10.1 days, it could be 10.11 days, and so, right? So the lifetime is not an integer, right? The lifetime would lie in an interval over here, right? Interval would start at 0, including 0, right? And you you will have a boundary lifetime, right? But uh, even if you do have a boundary lifetime, right, which you probably can't really tell at this point, right? Say if the boundary lifetime was say 1,000,000 days, right? That would still be an interval, right? And because it's an interval, right? Interval of on your real number line, that means your possible values of the random variable is now countably infinite, right? And if you have a random variable where your possible values are in fact countably infinite, right? Or the values of the random variable form an interval such as this, right? Then such a random variable is called a continuous random variable, right? So this over here, when we say we're looking at lifetime of compressors, this random variable defined over here, this is a continuous random variable, right? And the idea here is that you possible values are continuous, right? It is ranging continuously, say from 0 um, onward, right? Discrete random variable, it's not continuous, right? So for example, this discrete random variable, its possible values would be 0, 1, 2, right? And there's nothing in between, right? It's not to say that there's 0.3 or 0.33 or something like that, right? It's discrete, right? Here, you the values of the random variable range continuously from 0 onward.